So we're going to get into compositions of functions. It's very similar, but just a little bit different. So today, the words we're going to learn are what are compositions of functions, and it's basically the act of applying one function after another. And so we're going to see what this looks like. So compositions of functions. A composition of function is applying one function after another. The new function is called a composite function. So basically, we start with two original functions, an fx and a gx, and then we take the composite of that, and that creates a new function or a new equation. It can be written different ways. For example, it can either be written to look like this, or G is the composite of F. Okay? And so basically, because Fx is the innermost function, more specifically, it is the function that is on the inside of the parentheses, that's where we start. Okay? And so it's important to realize that compositions of functions do not mean multiplication, but rather they mean, and we're going to see what this looks like, it means inserting one function into another and then creating a new function out of that. So more specifically, G composite F is not the same as G times F. Okay? It is not the same. So that's a big takeaway here. It is a composite, and so we are going to do the composite. We're not going to use the operation for multiplication in this instance. We're going to look for the composite. So that's an important thing. Okay? And so first what I want to get into is mapping diagrams. And we're going to look at when we need to use a mapping diagram to find the composite. So more specifically, a composite, for example, one second. For the composite, F, G, X, or this can also be written as F composite G, X, because we're going to put G into F. A thing you're going to recognize is that your domain for G, and then you have your range for G. So you have your domain for G, you have your range for G. Well, what you're going to realize is the range of G is also going to be the same as the domain for F. And then F is going to have its own range. So again, range are our X values, what we input, and then our range is going to be our Y values, our output. Okay, and so let's see what this actually looks like. So say we're trying to use a mapping diagram like the one we saw before, and what we're trying to do is find what is F composite G of X when G is 3. So basically what this means is what we're going to do is we're going to identify when G is 3. And what we see there is that when G is 3, the new domain of F is 9. And if the domain of F is 9, then our range of F is 2. And so basically our answer here would be 2. Because what you're going to do is you're going to follow along that line and identify what F results in its range. So remember, this is the range of F. This is the domain of G. So what we insert into G, this is the resulting range of G. But it's also the domain of F. So basically, whenever we have a mapping rule, all you would have to do is identify what is G equal to whenever we put in the domain value 3 for X. And what you see there is you follow that line all the way across, and you'll see that F results in 2. Okay, but that's just when we're using mapping diagrams. And so we're going to see what we're actually going to end up with when we have to create a whole new equation. Does anyone have any questions so far?
No, ma'am.
Okay. So now we're actually going to get into composite of functions, and very similar to what we saw in function operations. At first it's going to be like, why are we doing that? That's a little funky, but it's all going to make sense in the end. So basically, here we have two different rules, right? We have F composite G and we have G composite F. And so it's very important that we don't confuse those, because you cannot switch the order and get the same answer. So for example, the answer of F composite G will not be the same as G composite F. Okay, but I'm going to show you exactly what it even means to be a composite. To be a composite, it basically means, okay, let me start here. So we saw before that when we have an F and we have an X, that means to insert X into F. Same thing as if we have F2. Whenever we have F2, what we know, or what that means, is say that we have X minus 7, like we do here. Well, if we have F2, then that means we know that we input 2 for X, and then our resulting value will be our answer. So now we'll take 2 minus 7, and that will give us -5, right? So we know that whatever is in the parentheses is what we substitute in the equation of Fx. And so the same thing goes for composites, except instead of putting in a value like 2 or X, we're actually putting in an entire equation. And so that's what's going to be a little funky, but it is actually something you can do. So, for example, this is supposed to say F. Okay. So basically what this is saying is that we have our regular equation, Fx, but what we're going to insert for X is whatever the equation of Gx is. So that basically that's what a composite is. And so I'm going to show you how to do that. And so basically what you're going to do is you're going to identify what even is Gx. Well, Gx is x squared, like we see right here. And so what you could do is you could actually substitute the equation into there where it says Gx, because they are one and the same. 1 second. And so now what would this actually look like? Well, let me show you. So now we have Fx squared equals, what is our Fx? Our original Fx is x minus 7. And now what we can go ahead and do is plug in x squared for x, like we do whenever we have a value for x. All you do is plug it in. So and what we see there is we result in a new equation, and that's the equation which will represent our composite. So basically what we're doing is, instead of inputting an actual variable, for example 2, what we're doing here is we're inputting an entire equation into x. So that's what we did here. We substitute x with x squared because that is the equation that we need to insert for our value of x. Okay, does anyone have any questions on how I got x squared minus 7? Okay, so why is it important to know what order you're going to? Is because, say we have here, we have Gx, and what it's telling us is to insert the equation f of x into g of x, and so that will look like g f of x, x minus 7. And so now we can actually do this. What is our original g of x, x squared? Okay, so what is this telling us? So it's telling us to insert this equation. for x, and so we can go ahead and do that. X minus 7 squared. What is x minus 7 squared? Well, you did this, and now you can do FOIL. And what you get as a result is x squared minus 14x plus 49. And so as you can see there, is the order matters, because if you don't follow the specific order, then you will get two different equations. And so order matters in this sense. Any questions about this? So you cannot switch the order and get the same answer. That's exactly what we see here. Okay. Okay, let's look at this a little further. Okay. So what we're using here is method 2 for evaluating composite functions, which in my opinion is the easiest method. And it is basically finding the composite rule. So our composite rule tells us that when we have something that looks like this, what is this basically telling us? Well, it is telling us f, g, x. Okay, the first letter would go first, so f, and then the second letter is what we're inputting in, and so that would be r. Gx. And so now let's go ahead and use this composite rule to solve for this problem. Okay. And so basically, what is fgx? Well, remember this composite rule to solve for this problem. Okay. And so basically, what is fgx? Well, remember, it's basically the same as taking f and inputting the equation of gx in for the x of f. So f equals 6x plus 7. What is this telling us to do? Well, it's basically telling us to take our equation g of x and substitute it in for x. And this will result in 3x plus 7. Now there's something a little different about this problem, and the thing that's different about this problem is it's actually telling us to input a variable -2. And so we're going to do very similar to what we did in the function rule. First, we're going to create the equation, and now that we created the equation, what we can actually do is plug in that value of x, -2, into our x of this equation and solve. So that's very similar to the function rule. The first thing we did was create our new equation. Once we create our new equation, we can solve for the problem. And so basically what we'll do is we'll take our new equation and now plug in -2. And what we'll see is we get 1 as our answer. Okay, so the first thing you want to do is find your new equation using the composite rule. And if you are told to do so, then you go ahead and substitute your value of x into the new equation. If you're not asked to substitute a value of x, then all you have to do is find a new equation and then you're done with that problem. Okay? Does anyone have any questions about this? Questions, concerns? Okay. And now we're going to look at one more thing. And this one more thing that we're going to look at today is we're going to learn about restrictions on the domain. So basically a restriction on the domain it tells us what our domain restriction is. So for example, sometimes we see problems where it tells us that the domain is all real numbers, so the range is all real numbers, or the domain is x greater than 3. I'm sure you've seen these problems before. And basically what those domain restrictions do is they tell us if we were to graph this function, what is the bounds of the domain that the domain or the x values can exist in. And so what we're going to do is we're going to look at how to find these domain restrictions whenever it comes to a composite function. So let's go ahead and get into this. So there's two ways to go about finding our domain and two methods. Whatever your preferred method is, depends on you. I do have a preferred method. I'm going to show you both because it really just depends on what your preference is. But basically what we're doing is we're finding the domain restriction or what all the possible x values can be. And so the first way that we can find this is we can find the individual function domain restrictions and then put those together to find what the composite domain restrictions are. And so more specifically, what I mean by this is we'll find the domain restriction of the equation fx, and we'll find the domain restrictions of gx, and then we'll see where the domain restriction is for whatever our new composite function is, our new composite equation is. And so basically what you would do is you would go ahead and find the domain restriction of fx. And the way you would do that is you would take the inside of the square root and you would go ahead and solve for when x gives us 0. And so when x gives us 0, the way we can do that, add 3, x is equal to 3, okay? And so now what we can do is we can also find the domain restriction of gx. And so basically we would do the same thing, x plus 5. And what we want to do is identify when it is equal to 0. And it is equal to 0. When x equals 5. And so now what you want to do is you want to identify what their commonality is. And the way that you would do that is you would find the domain restriction of gx whenever gx is equal to the domain restriction of fx. So basically what that would look like is x plus 5 equal to 3. So basically what I did is I took my gx, this value right here, put it right here, and then I took my domain restriction that I found of fx and put it right here. And what I want to do is solve for this to find where the commonality of those two are. And the way we would do that is you want to isolate x, and we'll see that x is equal to -2, and so that is our domain restriction. More specifically, x would be greater than or equal to -2. Okay, so that's how you take the individual domain restrictions and then find the commonality. Now, if this seems too complicated for you, there is another option. So let me show you that other option before I take any questions. So the next way to identify this is to actually find the composite rule. So find the new equation and then take the domain restrictions of the new equation. So basically we would do what we did before. So what is this basically telling us? Well, it's telling us to take the fx equation and input x plus 5 for x. And so we'll go ahead and do that. Which is equal to okay, and so this is our resulting equation, our composite equation. And so now what we can do is just take the domain restriction of this equation. And the way we would do that is find what x needs to be in order to make that equal to 0. So minus 2, x is equal to -2. So as you can see, we get the same thing, and then we'll just input greater than or equal to. And so as you can see, you get the same domain restriction, it's just whatever your preference is for solving it. So you can take the individual domain restrictions of the individual equations and then find their commonality like we did here. Or you can find out what the new composite equation is, and then once you do that, take the domain restriction of the composite. Okay? Are there any questions about this? And again, my preference would be to do this because it's a lot easier to find the new equation and then find the domain restriction of just one equation. Okay? But does anyone have any questions?
No, ma'am.
Okay. So what did we learn today? Well, we learned what a composition of function is. And a composition of functions basically just means instead of substituting an actual variable into f or g, depending on what we have. So here we're inputting a variable to f. If it looked like this, then we'd be inputting a variable into g. But basically a composite is just inputting that variable as a whole equation rather than just a single number. And that equation that we input is whatever in this instance our g-axis and whatever in this instance our f-axis. So that's what a composite is. And then we also learned how to identify domain restrictions depending on whatever method you want to use. So if you are asked what is the domain restriction of a certain composite, you can choose whatever method you prefer to solve for that. Are there any questions about what we learned today? And very similar to what I did for function operations, I'll put a document which kind of synthesizes this and makes it a little bit simpler. But basically, this is what we get for composite functions. Okay, any questions? And then we'll go have some problems tomorrow. Okay. Okay, if there's no other questions, you guys may log off and I will see you guys tomorrow. Bye, guys.
Bye, Miss. Have a good day.
You too, bye.